All right. Any questions, concerns, etc. before we get started today? Yes.
Did we ever see a date for test 2?
Yes. Let me pull up the calendar real quick.
It's November 17th.
The week of the 13th through the 17th, but yes.
Yeah.
Let's see. November 13th through 17th. So, during lab time this week, the week before Thanksgiving break, if that helps. This week is going to be chapter 8. Next week is going to be a short chapter on pressure, and then segueing into test review for this test, and then done and over with before Thanksgiving. Bless you.
Thank you.
Bless you.
Thank you.
Any other questions? Yes, those are the 3 times I'm giving a 1500 exam, and you can come to any one of them. It doesn't have to just be this class's one-time slot. You can come to any of the 3.
Is that for the final?
Yep. It's one of the 3. It's not like all of the 3. It's not a multi-part exam. You just pick one. Pardon me. So, last time we looked at the universal law of gravitation and how it can act as a centripetal force. This led us to looking at what I call an orbit question. We looked at, and I'll just put it back on the board. We calculated how much force of gravity the Earth exerts on the Moon, and then used that force of gravity as a centripetal force to find out the speed at which the Moon is moving around the Earth. That's where we left off, right? I'm going to point out that this type of interaction is the cornerstone of what I call orbit questions. I want to point this out because there's orbit questions on the relevant homework. There is going to be one orbit question on test 2 and one orbit question on the exam, sorry. Homework, test 2, and the exam will all have one orbit question on them. And the main point of this type of question is that in space, gravity acts as a centripetal force. And so I put in your notes, even on your formula sheet, this is something that can happen. Gravity is acting as a centripetal force for an orbiting object in space. And if that happens, you can set the gravity formula equal to the centripetal force formula, which could allow you to do things like find the speed that something rotates at, or even possibly the radius that something orbits at. So I would definitely include in your notes that this is a type of question that can occur. Orbit questions is what I would call them, when one object is orbiting another object in space. Moon around Earth, satellite around Earth, Earth around Sun, things like that. And I find this an interesting interaction because the R's in every version of this formula, you got R squared in the gravity formula, and then the 2 different versions of the centripetal force formula. This version is n times centripetal acceleration, but using the linear formula for centripetal acceleration. This is using the angular formula for centripetal acceleration. The R in every version of this is the same R. It's still always referring to the distance between the 2 objects, namely their centers. So I use the same letter because it is actually referring to the same thing. And that means that it can cancel out depending on which versions you're using. So same R across all these versions, every side of this interaction. Likewise, the mass of the centripetally accelerating object is going to be a repeat of one of the two masses in the gravity formula. Because this formula is talking about the gravity between two objects, and one of those two objects is orbiting the other, which means that the orbiting mass would go here again. It would go here because it's one of the two objects creating gravity, but the orbiting object's mass would get reused here. And it's always the orbiting object, because that's the object that is undergoing a centripetal acceleration around the other. So in this case, which object is doing the orbiting? Which object is centripetally accelerating around the other? The moon. The moon centripetally accelerates, orbits around the Earth. So in this version, what we did on Friday, the mass we used on this side was the moon's mass again, not the Earth's. It's always the mass that is doing the orbit, which actually means, since moon mass is on both sides, that can cancel out in some weird ways too. So it's an interesting interaction of the formulas, and since this will show up, I do highly recommend, first of all, remembering this is something you can do, and remembering that it will come up in any orbit type question. There will be one of those on the test, which also means there'll be one on the practice test, and on the final, and on the practice final. Speaking of practice, let's practice it one more time before I teach you something new today. Instead of the moon, we're going to look at a meteor that is approaching the Earth. 500 kilogram meteor is approaching the Earth. It is rocketing towards us at 7,650 meters per second, which is very fast. That's about 15 to 20 times speed of sound. And we need to figure out, because we work at NASA, we need to figure out what this object's orbital radius is going to be. We need to figure out at what distance around the planet it is going to try to orbit the planet. Whenever scientists notice something like this approaching the Earth, they always have to track its trajectory, see if it's going to hit the Earth, see if it's going to orbit the Earth, or possibly get curved around by our gravity. So they have to check these sorts of things, to make sure that we don't get extincted like the dinosaurs. So we know the mass of the rock, it's heading towards Earth, and we also know Earth's mass. So we know the mass of the two objects. We know how fast the rock is moving. We need to figure out what its orbital radius is going to be. So assuming that the rock orbits the Earth's gravity on the rock will act as a centripetal force. So this is one of those scenarios we would look at this interaction, setting the two equal to one another. Formula says that on the gravity side, big G times m1 times m2 over r squared. On the centripetal force side, this force is going to act as a centripetal force on the meteor and cause it to orbit at a certain speed at a certain distance from the planet. We need to figure out what that distance is. So our unknown right now is r, every r. It's the same r in all those different places, but in all places the r is, we don't know what it is yet. So we have to figure it out. Since we've been told linear speed, I'm going to recommend we use this version of the centripetal force formula. We're not going to need this one this time around because we don't know its angular speed. So I'll just erase that one and stick with linear for the time being. On the gravity side, start filling in what we know. Big G is always 6167 times 10 to the negative 11th. For M1, we'll plug in the mass of Earth, which is always 5.98 times 10 to the 24th. You don't have to memorize that number. If you ever need it, I'll make sure you have it. I certainly don't have it memorized. M2 is the mass of the meteor, which is 500 kilograms. And that is over r squared. Again, r is what we're looking for this time around. That's the gravity side. Any questions? Yes?
What is that number on top of 10 you said?
This one?
No,
This one? That's negative 11. I'll back up real quick to look at the slide with the formula on it. Universal law of gravitation, big G is defined always as 6.67 times 10 to negative 11. And that is on your formula sheet. There. Does that answer the question? Now on the centripetal force side, again, the orbiting object's mass goes here, so is that going to be the Earth or the meteor? Meteor, very good. Usually the smaller thing spins around the bigger thing. So the M on the right will be the meteor's mass again. Velocity, meteor's moving at 7,650, which does need to be squared. And then R is still the unknown we're looking for. It's the same R on both sides. So it's thankfully just one unknown. We just have to get creative and condense it all on one side. But this is the sort of thing that NASA goes through to figure out what distance something is going to try to slingshot around the planet at. Any questions arriving at this point? All right. Now, because we have the meteor mass repeated on both sides, and because we have the same R on both sides, we have some interesting cancellation shenanigans we can employ. For one, both sides have a 500 multiplied into their numerator, and that means it can just go away on both sides. This implies that any meteor of any mass would actually do the same thing as long as it's moving at the same speed, regardless of its mass. So that's a fun fact. It could be a teeny tiny rock, it could be a very big space station. It would have to move at the same speed to orbit at the same distance, all the same. Furthermore, we can bring r squared over into the numerator of the right side. That would give us r squared over r, which is just going to turn into normal r. I'll try to demonstrate that real quick. A lot of big numbers to have to rewrite in these sorts of questions. The 500's canceled, so I'm just not going to rewrite them again, but they do cancel out. They're in the numerator of each side. Divide both sides by 500, they just go away. On the right, so I'm just bringing r squared over to show what that looks like. 7,650 squared over r times r squared. So we brought r squared into the numerator of the right side. R squared over r is just r. So that kind of handles the needed compression of those numbers pretty nicely, in my opinion. And lastly, just need to send the velocity squared over to the other side. That would be 6.67 times 10 to the negative 11. 5.98 times 10 to the 24th over 7,650 squared, and that will tell you this rock's orbital radius. Its distance from the center of the Earth, not from the ground, from the center of the Earth. That's an important disclaimer. Do this right, please correct me if I'm wrong. That should come out to be 6,815,600 meters from the center of the Earth, which, for simplicity's sake, is about 6,800 kilometers from the center of the Earth. Yes?
So we didn't have to use the radius that it gave us, was it just giving us something to compare?
Oh, this radius?
Yeah.
Yeah, this part is just to compare that answer to Earth's radius. Note that the answer we got is bigger, which means that this object will actually orbit the planet above the ground instead of plowing into Earth's surface. If the object wants to orbit at a radius smaller than the size of the planet, that means it's gonna hit us, which is bad. In this case, that radius is bigger, which is good for life on the surface. However, that does mean it's gonna orbit at about 350 kilometers above the surface. Sorry, 450, which is about the height of the space station, which is not good for the astronauts. So, this meteor won't extinctify life on the planet, but it might endanger the astronauts. So, action would need to be taken. How does this feel? All right, so once again, please just note, this is an orbit type question. There will be one of those on the upcoming test. We will continue to practice them as needed. Now, for the rest of today, I would like to begin chapter 8, which it's still about rotation, so it's not like all new, it's just the next step. But I want to begin talking about the next rotational concept because that concept is torque, and our lab this week is a torque lab. So, any objections before moving on to that? Okay. Now, once again, chapter 8 is just more rotation. So, what chapter 8 will specifically be about is looking at even more rotational concepts and how they relate back to the same linear concept we've been talking about all semester. Because we've already looked at how displacement, velocity, and acceleration have angular counterparts. You can use them to describe either form of motion as long as you change from meters to radians. But it turns out the same is true of pretty much anything related to linear motion. Force, momentum, kinetic energy, they all have to do with linear motion, and they all have angular counterparts. The only one we're going to look at today is torque. And torque is actually one of those physics concepts that people have a pretty good understanding of because you've used it every day of your life. I can almost guarantee that. Outside of a physics class, how many of you have heard the word torque before? It is spelled T-O-R-Q-U-E. Okay, a couple hands. Growing up, I heard it most often in like car commercials, which is actually pretty apt because torque is the angular counterpart of force. Linear force causes objects to linearly accelerate. If you want to make something move, you have to push it. And that causes it to begin moving, correct? Well, it turns out torque serves the same role, just rotationally instead of linearly. Newton's second law says net force causes mass to accelerate. Similarly, torque, rotational torque causes objects to rotationally accelerate. Now to back up slightly, we're used to thinking about linear force, I hope, right? If if I want to push this bike wheel around, I have to grab it and I have to exert force on its mass, and that will cause it to start accelerating in the same direction of the force. But note, right now, I'm grabbing the wheel by its axle, which is basically its center of mass. And if I exert force directly on that axle, the wheel doesn't really spin, it's just translating through space in straight lines. So it's not rotating, it's just my linear force is causing linear motion. If I want this thing to spin, I need to use my linear force to generate torque. And the way that you generate torque is by exerting your force at a radius away from an axle of rotation. For this bike wheel, what that means is, rather than applying my force on the axle, I have to physically exert it elsewhere, at a distance away from the axle. And that causes it to spin. And you have done this in some way, shape, or form every day of your life since you started walking and picking things up with your fingers. If for no other reason than because of these things. I'm literally just pointing at the door right now. This is an object with an axis of rotation, namely the hinges. And if you want to open or close this door, where do you put your hand to apply that force? Either on the doorknob, yes, or somewhere within this vertical axis, somewhere along this line, which is some radius away from the hinges, correct? Now doors spin. You don't really want the door to move in a straight line. If I push the door in a straight line, it would rip off of the hinges and fly away. I don't want it to move, linearly accelerate. I want it angularly accelerate. I want it to spin on the hinges. So I need to generate torque. And to generate that torque, I apply force some distance away from a pivot. And that's why the doorknob is here, as far away from the hinge as it can be placed. And even if the doorknob wasn't there, you would still know, grab this end instead of the hinge end, right? Like at this point, you've opened enough doors to just have that understanding buried in your brain, right? That's because, looking at the formula again, the further away from the axis of rotation you exert your force, the bigger this R number is, the more torque you generate. And the more torque you generate, the easier it is to make something spin. Akin to the more force you exert on something, the more likely it is to move and move fast. So, to move the door, you grab the edge of it furthest away from the hinges to increase that radius. I encourage you to try opening or closing a door by exerting a force closer to the hinge and see that this does not make life easy for you. This is hard and it's not working very well. This is kind of hurting my fingers. It'd be even worse if you were pushing on the hinge directly. That's not making the door move at all. So, any object that can spin, you generate torque by exerting that force a distance away from the axis. The closer to that axis, the less torque you generate. The further away, the more torque you generate. But it's not just doors that do this. It turns out most things that humans have invented to use with our hands involve torque somehow. For example, wrenches. Because what is the purpose of a wrench except to make something spin, right? We have a bolt, we want to make it spin so that it actually bolts into whatever we're attaching it to, right? We have to make it spin in order to do that. If you grab this bolt with your bare hands, have you ever done that and noticed that it's not all that fun? Especially if you're trying to loosen it, that sucks. And that's because if you just grab the bolt, the radius of rotation is just the width of the bolt. And those suckers are usually pretty tiny. Instead, we have invented wrenches. And the nice part about wrenches is they have a handle that is much longer than the bolt is wide. So let's take a 1 meter long wrench and exert 12 newtons on the end of the wrench instead of by exerting 12 newtons directly with our bare knuckles on the bolt. That 12 Newton force applied 1 meter away from the bolt will generate 1 times 12 Newton meters worth of torque. A lot more than 12 newtons applied directly on the bolt, which is like 5 centimeters across. 12 times 0.05 is a very small number. How's this feel so far? All right. If the wrench was twice as long, like if it was 2 meters long, and we still exerted 12 newtons of force on it, how much torque would we get? 24. 2 times 12 is 24. And again, I don't know if I said this out loud yet, the unit of torque is newtons times meters. Actually, I haven't even addressed the symbol for torque yet, my bad. This is our new formula for torque. Torque equals radius times force. Radius is still measured in meters, force is still measured in newtons, and that's where the unit comes from. They didn't give it a unique unit, but at least the unit they gave it makes sense. And the variable for torque, this kind of looks like a fancy script T when a computer generates it. When I write it by hand, I try to make it look a little fancy. This is supposed to be a lowercase Greek tau, T-A-U. I don't think there's any Greek life on campus that uses tau, is there? No. Just going to show the difference between all of those letters. Uppercase tau, which is used for period of oscillation in physics. Lowercase tau is torque. Uppercase T and lowercase t, which is time. So all these letters are used for different things in this class, and that's not confusing at all, is it? So this one's torque. I don't know, it kind of looks like T with a fancy hat, or maybe like it's dancing and those are its arms. I'm really just making sure you know when I say tau, I'm referring to torque. So torque equals radius times force. If you want to increase the torque, you want to increase the strength of the rotation, you either have to use more force or you have to exert it from further away. Once again, if you have physically a longer tool, you'll just generate more torque. And that's why really big pipe wrenches, like physically with 1 and 2 meter long handles, exist for those really tough steward jobs. And it turns out most tools, not even just wrenches, use this principle. That includes screwdrivers, and it also includes baseball bats and a surprising amount of sports equipment. Because baseball would be a lot harder if you just had to punch the ball out of the air. I know this from experience because I tried to punch the ball in volleyball and it didn't go well in high school. What the bat does is, rather than applying the force directly on the ball, if you use the bat, that force is applied a distance away from your hands, you generate torque and you kind of multiply your output. And you also don't damage your knuckles. So baseball bats, golf clubs, tennis rackets, crowbars especially, and even swords and axes all use torque. Pretty much anything you pick up with your hands uses torque somehow. So it's everywhere, and I find that this is a concept that people have a pretty good, like, subconscious understanding of. The hiccups are just putting words to it. How do you guys feel so far? All right. We're going to spend the next couple of minutes talking about some of the weird quirks of torque that I want to make sure you're aware of. First is actually this little parallel symbol in the perpendicular formula in the symbol that I haven't acknowledged yet. That symbol is there because the force you exert has to be perpendicular to the radius of the object. What I mean by that is, if I take this wheel and I want to make it spin, I have to generate torque on it to do that. I'm grabbing the edge of it. Note that where my hand is applied, the rotational radius from here to the axle is, within the x-axis, points level within the horizontal plane. If I exert a horizontal force on this wheel, say I pull to the left, oh, my left, your right, is that ever going to make the wheel spin? No. If I push inward to your right, your left, is that ever going to make the wheel spin? No. So if the radius is horizontal, a rightward or leftward force are parallel to that, and those can't generate torque. To generate torque, I have to grab the wheel and pull it either up or down, which are perpendicular to that radius where I was grabbing the wheel at. Same is true for the door, actually. And again, you likely have a good subconscious understanding of this as well. If I want to move this door, I would grab it and I would push either this way at a right angle to the body of the door, or this way at a right angle to the body of the door. If I try to pull parallel to the body of the door, I'm either going to pull in this direction, and that's not accomplishing anything, or push in this direction, and that's still not accomplishing anything, other than making me look very silly. That. And I might fall over. So, to generate torque correctly, the radius and the force have to be perpendicular to each other, which means that things can get kind of weird if the forces aren't totally perpendicular to the body of the object. Because if you've ever seen someone get really frustrated with a wrench, like it's really stuck, they might try to grab it at a suboptimal angle and just pull towards themselves however they can. And in this drawing, that wouldn't work out so great. Say we're still exerting 12 newtons of force and it's still a 1 meter long wrench. But not all 12 of those newtons are perpendicular to the wrench's body. Only some of them are. So, flashback to trig real quick. We'd have to figure out how much of that torque is perpendicular and use that. Sorry, how much of the force is perpendicular and use that. So if that's 50 degrees, the leg that is perpendicular to the body of the wrench would be the opposite. So sine of 50 is the perpendicular leg over the total. 9.2-ish of those newtons are perpendicular to the wrench, so we would use that instead of the full 12. So the angle not being right has already reduced our effectiveness. So just a general tip, if you're ever using a wrench, or even a hammer really, or again any tool, make sure the force you're using is perpendicular to the length of the body of the object. And that the object's handle is as physically long as you can manage if you want to get as much torque as possible. Again, I've said that pretty much every tool uses this somehow, but this is the entire reason crowbars were invented. Because manhole covers are very purposefully heavy, but with a very long crowbar, you can generate torque and cause the thing to rotate, and you can slide it out of the way. And you want the crowbar to physically have as big an R as possible to make that as easy as you can. There's an old quote attributed to Newton that says if you have a crowbar, I'm paraphrasing, a crowbar long enough, you could actually move planet Earth. And that is true. It would just need to be like a couple light years across. So at that point it would have its own gravity and you'd be living on it, but it's possible. So, you guys feel okay about the perpendicular thing? All right. Now, the other quirk that I want you to be aware of is how net torque works. Remember how net force determines net acceleration and how all the forces on an object can add up together? The same is true for torque, because as it happens, if a linear concept is a vector, its angular rotational counterpart is also a vector. So since forces can all add up together and possibly add up to zero, torque is also capable of the same thing. And since torque is the counterpart of force, net force causes net acceleration, and therefore a net force of zero causes a net acceleration of zero. Net torque causes net rotational acceleration. So if you want something to start spinning, you have to exert torque on it. And if something isn't spinning, that means that the net torque on it is zero. Like how if something is not linearly accelerating, the net force on it is zero. So, if something is not angularly accelerating, that means that all the torques acting on it add up to zero. And torques can add together like forces can. We call this rotational equilibrium. If an object isn't rotating, like the door is right now, that implies that the net torque on the door is zero. Currently, all the torques on it are balanced and add up to zero. And that is true for every object that is not currently spinning, even if it's not normally capable of spinning. Any questions so far seeing the comparison here between torque and force? Okay. Now, in my opinion, where this gets kind of weird is the fact that linear force can point in all kinds of directions. We live in 3D space, and you can point in any possible combination of those three axes. Torque really only has two directions, those being clockwise and counterclockwise. Those are the only two directions you can spin in. So there's lots of directions for force, but torque and also most rotational vectors only have the two, clockwise and counterclockwise. So rather than having to think about a bunch of different axes all having to add together to zero, like with linear force, torque, you just need to make sure that all the clockwise torques cancel out with all the counterclockwise torques. You can still think of it as net torque equals zero, where the clockwise ones would say be positive and the counterclockwise ones would be negative, adding up to zero. But another way you can think about it is the net counterclockwise torque must equal the net counterclockwise torque. Either approach here technically works. Like this is derived from net total torque equals zero. So all the left torques cancel out with all the right torques. As long as that's the case, the object should not rotate. And we're talking about this now because lab this week involves trying to keep objects from rotating, trying to prevent rotation. If you want to prevent rotation, you need to make sure that all the torques cancel out like this. And the type of situation that lab is going to have where this is the case is teeter-totters. Now lab doesn't involve physical playground teeter-totters. We're going to build balance beams out of meter sticks. But kind of flashing back to childhood perhaps, this is really just weaponized, well not even weaponized, this is just torque turned into a game. That's all a seesaw is. Because a seesaw has a fulcrum, it has a point that it can rotate around, and it will rotate if it is imbalanced, if the torques on it don't add up to zero. But if the torques on it do add up to zero, then it stays still. And please let me know if you also played this game when you were a kid. Me and my cousins would always try to get this thing as closely balanced as we could for as long as we could. Like, you know, each of us would have to sit in a different place to make it happen. Since I was the oldest and therefore the heaviest, I just had to stand on the middle, shifting my weight on either side. I wasn't the only one that played this game, was I? Okay, cool. We're gonna put math to that right now, basically, and then lab this week will further put more math to that. Basically, when someone sits on either side of the seesaw, their weight is going to be the force that generates torque. So we've got two kids in this case here, a 30-kilogram kid on the left and a 60-kilogram kid on the right. The left kid is going to generate counterclockwise torque, if you just think about from our current perspective. This would make the force points down, and so that's going to try to make the whole thing spin counterclockwise. Meanwhile, the kid on the right side, their force also points down, but it's on the other side of the pivot, and that would try to make everything spin clockwise. So the torque that each kid is making opposes the other. One of them's producing clockwise pointing torque, the other's producing counterclockwise pointing torque. So they are opposing each other. And if they want to play this game where they try to keep the seesaw level, they need the torques they generate to cancel out. And we can use this fact, the idea that the clockwise torques have to cancel out with the counterclockwise torques, to try to figure out where they both need to sit to make that happen. Net torque counterclockwise must equal net torque clockwise. And I set the formula up like this since the left kid is making counterclockwise torque and the right kid is making clockwise torque. Yes?
Are like counterclockwise negative things?
You can think of them as negative, because since they are opposing directions, one of them does normally need to be negative. But I like setting it up this way, since the forces technically both point down, and somehow the same direction of force makes different directions of torque depending on which side you're sitting on. So I like setting it up like this, because that way, like, it's just setting the two directly opposed to one another, rather than one of them having to be negative and they add up to 0. But if you did have them both on the same, and actually, if they were both positive on either side, and we brought one over to the other, that would make it negative, they'd add up to 0. So one of them does normally need to be a negative number, but we brought it over and that kind of canceled out the negative sign. Now this is just how I do it. Equally valid would be net torque equals 0. You add the two torques together and one of them would have to be a negative number since they do point in opposite directions. Either method works. I like this method because I kind of visually like seeing, you know, left kid on the left, right kid on the right. So just kind of your preference, which method you prefer. But whichever your preferred method of thinking about it is, each kid is generating torques that oppose each other, and we can use that to our advantage to figure out where this kid, left kid, has to sit to balance out the system. Because right kid, the 60-kilogram kid, is already sitting at the 1 meter mark, so we got to figure out where kid 2 sits. And they can't change their masses, but they can change where they sit. So, there's only one torque on each side. There's only going to be one clockwise torque and one counterclockwise torque. Lab this week will involve scenarios with more than just the two. But for right now, it's just the two. On the counterclockwise side, we've got the left kid, because the left kid is going to generate the counterclockwise spin. So that would be, I'm going to call them radius 1 and force 1, and radius 2 and force 2. And that's just because there's one torque on each side. Each one kid is making their own one torque on either side of the seesaw. Now, we don't know kid one's radius, but we do know kid one's mass. And how does that affect the force that kid one is exerting?
Force of gravity.
Yep, it would be the weight of each child. So on the left, unknown radius 1. The force from kid 1 would be their mass in kilograms times their weight, times negative 9.8 to tell us their weight. Then on the right side, we do know kid 2's radius, and we also know kid 2's mass. So their weight would be 60 times negative 9.8. Note that the negative 9.8s just kind of cancel, which is good, gets rid of the negative signs. R1 times 30 is going to equal 1 times 60, which is 60. So R1, 60 over 30. And so, to kind of summarize what I'm sure a lot of you assumed at the very beginning, kid 2 has to sit 2 meters, or kid 1 has to sit 2 meters away from the fulcrum in order to double the amount of torque they create and equal the torque generated by the right side kid. Questions? So, lab this week will be more of this basically. You're going to physically build seesaws out of meter sticks and hang masses on either side, trying to get them balanced, and then mathematically calculate all the torques and show that they all cancel out. Or rather, use the level torque to try to figure out where something needs to go to balance the system. Yes?
For the week of test 2, you can come in during whatever lab time slot you have, or before.
Yeah, you can come for the week of test 2, which is November 13th through 17th, you can come in during a lab time period, like with test 1. You can come in any one of them, as long as your schedule allows for it. The main thing to remember is that there is no Thursday lab. Thursday is a myth. It's Monday, Tuesday, Wednesday, Friday.
And now we just going to
Yeah, like last time, the week of the test, lectures will be review focused. Yeah, will be review focused. So time to go over the practice test, homework, and anything else. Any questions about anything else? All right, make sure you bring these notes to lab, whatever that is for you, and have a great day.